Okay, so first lecture of the last chapter, organic chemistry. The main thing that we're going to focus on is really, well, a basic introduction to organic chemistry, interpretation of the structures, that kind of thing. And then really we have time for nomenclature for the most part. We don't have time, well, we organic chemistry is just a very large subject, and I want to take a minute with this particular slide, with this particular structure. This is a compound. It's a big old protein. Is what it is, and it's found in the mitochondria, and it's responsible for the synthesis of ATP, which is the energy source for enzymes in the body. And this is a very large, very beautiful protein that is responsible for the synthesis of probably one of the most important compounds in the body. And it's a molecular motor. Essentially, what happens is that you get a high concentration. This is a membrane down here that's sort of faded out, and part of the protein is in the cellular fluid, and then part of the protein is embedded within the membrane. And what happens in the process of, well, it's a citric acid cycle, and the use of the products coming from it to generate it's a pH gradient between one side of the cell membrane and the other. So there's a lot of protons floating up here. There's a low pH, and there's only there's a smaller concentration of protons down here, and so things tend to go from high to low concentration in this universe that we know, and it happens the same thing in the mitochondria. There's a potential across the cell membrane, and what the ATP, you can see the little channels inside of this molecular motor, and essentially allows for the flow of protons through the cell membrane. And in that process, there's actually a rotation of this portion of this enzyme. And the reason why I wanted to show this for organic chemistry is sort of give you something to look forward to, possibly. You know, the reason why you have to go through 2 semesters of organic chemistry before you do biochemistry, because these very elegant, very complicated molecules known as proteins, they are fundamentally held together and structured based on the organic chemistry you learn in the first 2 semesters of organic chemistry. You know, what they have here, the different colored regions are different subunits, different proteins that are coming together to form this more complicated protein. The interactions that hold not just the individual subunit together, but also the interactions that connect the two, and then ultimately the mechanism itself is really dependent upon organic chemistry, dependent upon the attractive and repulsive forces that you get to know as you go through organic chemistry. So this chapter for Gen Chem 2 is an introduction to organic chemistry. And I'm going to cover some topics here. Of course, we're not going to get to the point of understanding this structure. I have no intention of doing that. I want to start building your foundation in terms of understanding organic chemistry. And in my opinion, one of the important aspects is this the hybridization of the different atoms, and specifically the carbon atom that you see that thrown throughout organic chemistry. Because organic chemistry is essentially the study of carbon. What can carbon do within a molecule, structurally, and also in terms of physical and chemical properties. And because there's a big deal about structure-function relationship. If you want to understand, you know, not just that methane's going to burn, or this particular structure is going to react in a particular way in organic chemistry that you'll learn, the physical and chemical properties are dependent upon the structure, the geometries that you have of these molecules. And whether it's a very small molecules like we have here, or a really large one like we have here, there is a relationship between the structure of the thing and then its function. In this case, you know, the synthesis of ATP. Okay, So what is at the heart of the structure of a molecule? Well, one thing is this notion of hybridization. Now, in Gen Chem 1, you should have learned a little bit about hybridization. The main thing that I want you to know here, I guess there's a couple of things. One thing, being able to recognize, looking at a molecule and picking out what type of hybridization that we have here, and knowing that, like, for example, when you see this carbon here and there's 4 bonding regions around that carbon, I guess the main thing you saw from Gen Chem 1 is that you learned that it was a tetrahedral structure, and you can see that in the three-dimensional ball and stick figure for methane here. But the one thing to keep in mind when you start doing organic chemistry, if you get the privilege to do that, that the structure here is what's dictating the hybridization, and many times it's always a hybridization that I go back to when I lecture about organic chemistry in terms of trying to understand some of the chemistry of that particular molecule. And so just being able to recognize a hybridization, I think, is important for a student. And then the other thing about hybridization is understanding that notation. So, for example, and I'm not going to get into a lot of the nitty-gritty detail about this, but essentially the sp3, what that means is that there's one s atomic orbital and 3 p atomic orbitals that have been hybridized together to form now 4 what's called sp3, well, hybridized orbitals. And it's these orbitals that actually is involved in the bond formation that you see here. Just like the sp2 and the sp, the mixing of those atomic orbitals dictate what kind of structure that you have in front of you for a particular compound. So if you have a carbon atom, or really any atom in organic chemistry, and there's 3 bonding regions around it, then you're going to see, and then there's nothing else, there's no lone pair electron in this carbon, then you're going to have an sp2 hybridized orbital. And just like the breakdown with sp3, the sp2 means there's one s atomic orbital. There have been 2 p atomic orbitals from the carbon atom here that have been mixed together to form now 3 sp2 hybridized orbitals. If you want to look at the pictures of that, that's back in Chapter 9 for Brownell and May. I'm not going to ask you to draw the pictures or anything. Again, just being able to recognize what kind of hybridization that you have in front of you. A linear structure for a particular carbon atom is a sp hybridized orbital, and then look down here. We have a little bit more complicated molecule. It's not that much more. It's linear with respect to that carbon that's sp hybridized. And you can see the linear structure, 180-degree bond angle. But down here, what you have is this is actually an sp3 hybridized carbon. You have 1, 2, 3, 4 bonding regions around it, just like you have with the methane here. And so what you have is two carbon atoms beside each other with different hybridizations. And so being able to pick out a particular carbon atom and interpret it in the context of hybridization, I think is helpful here. And especially helpful for you when you do organic chemistry. Now these ball and stick models that you have here for these molecules, I do want you to be at least somewhat comfortable looking at the molecules and sort of, picking apart the molecule to understand what it's telling you. And I'm going to pretty much stick with just 4 different atoms. The red is going to be oxygen atoms. The black are carbon atoms. And then the white or the gray are hydrogen. And then the other one is the nitrogen atom, which is in blue. And so being able to look at these molecules, I think is important, because these three-dimensional structures of the molecule, it's really telling us more of a better picture of the three-dimensional shape. And again, structure-function relationship is very important when you start digging deeper into organic chemistry and biochemistry. When we start looking at, let me just fast forward a little bit. When we actually draw an organic molecule, we usually use this kind of notation, and it doesn't really tell us the three-dimensional shape, which it's, you know, there's some limitation. If we're on a two-dimensional plane like I am here on this computer screen, or on a chalkboard, or on a piece of paper, then we want a notation that's it's easier to draw. We can't draw that or that every time we want to build a structure. But when you look at these, for example, glucose here, you know, here's a black sphere, that's a carbon atom, and what you see is 1, 2, 3, 4 bonds around it. I know that that is an sp3 hybridized orbital. For the oxygen atoms, you know, it's useful, I think, to go back to the simplest molecule involved with oxygen, that would be water molecule, and that motif, if you will, that two bonds, two lone pair electrons, repeated many places in organic chemistry. And if you apply that reasoning to this structure here, you know, one thing about this, the ball and stick models, they don't explicitly show the lone pair electrons. But if you have a red oxygen atom and there's two bonds, two single bonds shown, then there's an additional set of lone pair electrons on the oxygen atoms there. If you have an oxygen atom with a double bond, well, actually, I guess we can go back to that first example. This is a structure known as formaldehyde, and I'm going to draw a different shape or a different way to show this molecule. And there you have, whenever you have an oxygen atom with two bonds, and there's two lone pair electrons with it. And so that's another structural feature. If you look back at how to draw Lewis structures, you may have very well drawn that. If you took my class, I know you did. So there's a couple of common bonding motifs or bonding themes that you see for oxygen that I want you to be familiar with. Nitrogen is less important. Don't even worry about it right now. Being able to interpret, know that nitrogen is in one of these molecules is useful, but I'm not going to get into the structural part right now. And one thing to notice is that the tetrahedral shape around each one of those carbon atoms, because you can look at any carbon atom in a molecule and determine its geometry and its hybridization. You know, back in Gen Chem 1, we traditionally stuck with a single, you know, one central atom, and then we looked at whether you had bonding regions or non-bonding regions around that central atom, and then we determined the shape of the thing and the hybridization of it. But now I want to expand that a little bit and have you appreciate that even though we have a more complicated atom, you know, at each carbon atom that we look at, we can treat it as one central atom, and we can see there's 1, 2, 3 bonds here, just like we had over here for the glucose molecule, and so I can say that's a sp3 hybridized carbon, and every one of these carbons are sp3. Whereas up here, if I look at that carbon atom, there's a double bond, and then 1, 2, 3 bonding regions total. That is like your formaldehyde back here. This would be an sp2 hybridized carbon atom. So again, looking at the molecule and being able to interpret, you know, what we have in front of us in terms of hybridization is something I want you to do. The last thing I want to point out here is another aspect, and I guess another way you can use structure to determine the hybridization scheme is that if you see a double bond, then what that means is that you have atoms that are sp2 hybridized. And it's consistent with our last definition. 1, 2, 3 bonding regions. For this carbon, 1, 2, 3 bonding regions. And the 3 bonding regions and the 1 double bond go hand in hand. And so it allows us to pick out that all of these carbon atoms that are attached in this with these double bonds here are sp2 hybridized, whereas this carbon atom with 1, 2, 3, 4 bonds around it would be considered an sp3 hybridized carbon. So again, looking at a molecule, interpreting what you see in terms of geometry, and then picking out what hybridization is what I want you to be able to do for these examples. Now I will tell you, like, naming and getting into some of the condensed structural formulas for these things is less important. We're going to stick with simpler molecules for that. Now, one of the the simplest approach to getting a little bit deeper into organic chemistry is to start out with hydrocarbons and to look at a series of these things and be able to interpret what we see. So one thing we have to worry about are these functional group names, and you will get to know these very well. What the functional groups are trying to do is they're trying to they're classifying the compound based on the common structural features. So it's a classification method. Based on common structural features. What's common to all alkanes is that you have this carbon-carbon single bond. What's common to all alkenes, you have carbon-carbon double bond somewhere in the molecule. You would classify this as an alkene. And notice that the geometry changes now. Notice this is our trigonal planar geometry with a sp2 hybridized carbon on both ends, and this is our tetrahedral geometry with an sp3 hybridized carbon. And so, also note the geometries here that are listed. And the main thing about geometries, if we go back to that second slide, is the idealized bond angle that's listed here. I don't expect you to know the deviation from one type of alkene to the next, like we have the 122 here. Again, it's the idealized bond angle for those different hybridizations that I want you to know. Now, what we're going to do in this particular section is to take each one of these, or this particular chapter, is to take each one of these functional groups and do a little bit of nomenclature with them. And the first one we're going to do here in a few minutes is concentrate on the alkanes and how we name them. And I'm going to save that until we get to that point. A couple other hydrocarbons, and I guess maybe it goes without saying, but when you see the term hydrocarbon, what it's talking about is that you have organic carbons, organic compounds when they only have hydrogen and carbon there. And there's 4 different ways that you're going to see that, and 2 of them are shown here, alkanes and alkenes, depending on single double bond. Well, we can also have a triple bond, and then one other type, this aromatic structure that I won't get into it much here, but we'll do it in a later section. But if it's a triple bond, and then notice the geometry that tells us it's an sp hybridized carbon on both ends here. And they change the ending. So it's a very common feature that you see for organic chemistry. There's a modification of the ending of the name to tell us what kind of functional group we have in front of us. So keep that in mind as we go through the process here. Actually, the only thing I'm going to say about the aromatic structures now is, well, one thing, it's a flat structure. It's a cyclic structure here. There's a more of course, any topic you get a hold of in Gen Chem, there's textbooks written about each topic that we're talking about here. So for our purposes, the main thing I want you to do is just recognize what an aromatic compound is, and then later we'll get into maybe some of the chemistry and nomenclature. But you have 6 carbons in a hexagon pattern, and then 1 hydrogen coming off at each carbon. Now this circle in here, I'm going to give a different notation for the benzene molecule. Or actually, you can use, it doesn't matter, what pattern of double single bonds you have there. And then there's also another notation for benzene, which is the one that I'll use. But any 3 of these, if you see that in a structure, then you need to know that that is an aromatic compound, and it has a different type of classification, has a different type of chemistry. Benzene is a fairly inert molecule. It's one reason why it's partly the reason why it's in the top 20 EPA list of a carcinogen. It's inert, it's flat, it can actually chelate it. It can squeeze itself in between bases on DNA and increase the mutation rate for that cell. That's not a good thing. Anytime you start messing around with the DNA and you you prevent it from doing what it normally does, that's a bad thing. And benzene's pretty good at that. But recognizing these notations is really what I want you to worry about in terms of aromatic chemistry now. Again, if you see one of these in any kind of structure, you need to know that that is an aromatic compound. And just briefly here, you know, what the way this is drawn, it's implying there's an alternation of an altering of the double single around the ring structure. And in reality, what happens is that these 3 pi bonds that are in this molecule, that is composed of 6 electrons. Well, in reality, those 6 electrons they're not localized between, you know, 3 different pairs of carbon atoms. They're actually spread out over the entire set of carbon atoms, pretty much equally, and that is shown in that particular notation. That's why I put a donut in the middle there. But again, we're not going to worry so much about this structure currently. The main thing I want to worry about here is how to draw the structures, and specifically, I'm going to worry about alkanes and then some variations of alkanes known as haloalkanes. Another functional group. We'll see that with the isopropyl chloride here in a second. Now, whenever I talk about a structural formula here, we've already seen one type, this ball and stick. Actually, we've seen 2 types. This is a space filled. I'm not going to give you something like this, okay? So I just put that here because I think it shows the structure pretty well and give you exposure to different type of structural formula. But in terms of the 3-dimensional shapes, it's these ball and stick that I'll have you do. But like I said, you know, I can't draw this every single time. We can't draw these things every single time, or it's not convenient to ever try. You get the computer to do it. You have programs to do that. When we're talking about a compound, and there's 2 that I want to go through here, there's the propane and isopropyl chloride. So I'm going to introduce a little bit of nomenclature here, but mainly it's this issue of the structural formula. What is the structural formula that we're going to use when we answer a question on the test, talk about it in class, see it here in the video lecture? And I guess the breakdown, it's I guess 3 different ways of naming these things. One is just the molecular formula. We've already seen these. I'm going to tell you right now, the molecular formula tells us nothing about the connectivity of the molecule. And so there's no information about connectivity. You know, how are the carbon atoms strung together? That's what I mean by connectivity. You know, when you have a long stretch of carbon atoms together, then well, 3-dimensional, it looks like a zigzag. It's just you know, sort of a linear a stretch of a structure. So a molecular formula doesn't tell us anything about exactly how it's connected. All it's telling us, like for the case of propane, and that's the one that I'm going to do first, it has this particular molecular formula. All it tells us, well, we can determine the molar mass, right? That's about it. It tells us we have 3 carbons and 8 hydrogens together, and tells us nothing about how the thing is put together. It's the expanded and condensed structural formulas that actually show us that. Now, I'm going to do the condensed structural formula first because it shows us everything about the molecule. And I'm just going to give this to you. This is the expanded structural formula. It's very explicit. Tells you about every single feature on the molecule. There's 3 carbons that are placed together in a line, and then it's a saturated hydrocarbon. All of the other bonds are taken up with hydrogens. They're all single bonds in this particular molecule. And you can see that if you count up the carbons, there's 3. If you count up the hydrogens, there are 8 in this particular expanded structural formula. So that's one way that the organic chemists use to to denote the connectivity of the atoms. This tells us explicitly how they're connected. Now, a more convenient way is the condensed structural formula. And what we do there is we take whatever is attached to each carbon atom and we condense it. And the form this will take on is that. So CH3, CH2, CH3. You know, whatever is on the right-hand side of that carbon atom tells us that, well, it tells us that 3 hydrogens are bonded to it. Bonded to that particular carbon. There's 2 hydrogens bonded to that carbon, and so on. And so it's a more convenient way to show the molecule. And to tell you the truth, I'm not going to do the expanded structural formula all that much. I do it here just to make the connection. It's easier to see all the features there. It's really this is what I'm going to use for this class. If you take my organic class, I actually use something called the bond line form, which is even much more brief than this. And to tell you the truth, it's more convenient to draw the structure, especially larger ones. Let me make a point about hybridization now. You know, we have each of these carbon atoms, and this is characteristic of an alkane. Each carbon atom has 1, 2, 3, 4 bonding regions, so I can predict that that is an sp3 hybridized orbital. So to form that structure, that carbon took its 1 s orbital and 3 p atomic orbitals and mixed them up into what's called hybridized orbitals. And again, the main thing I want you to do is just recognize the type of hybridization. To use them, take the organic class. Okay. Okay. So that's the case for propane, and then the isopropyl chloride. It has the molecular formula for that, C3H7Cl. Essentially, what's happening is that one of these positions of hydrogen has been removed, and then chlorine has been put in its place, is what we see. And let me just go ahead and do the expanded structural formula for this particular one, isopropyl chloride. There is an issue that we're going to deal with a lot, and it's this notion of a unique name is going to yield a unique compound, a unique condensed structural formula. Now, the expanded structural formula for isopropyl chloride will look like this. Now, for isopropyl chloride, like I said, you can see it in the molecular formula. One of these hydrogens have been removed and has been replaced by a chlorine. Well, there are 8 possible hydrogens that I could have taken off and replaced with the chlorine. Now, for the case of isopropyl chloride, it's one of these 2 hydrogens that's been replaced. Now, I'm just going to go ahead and tell you, it doesn't matter which one I replace here. It's going to yield the same compound. And it's going to yield this one here. Oops, yeah. And then Cl there. And so this is where the chlorine is placed here. We'll talk a little bit. This is referred to as an isopropyl group. That's a later lecture, so I'm not going to get into it here. Again, mainly want to introduce expanded condensed structural formula. Again, the expanded one is a bit long-winded, if you will. It takes a little more work to draw it out. Instead, what I'm going to do, I'm going to give you 2 different flavors, if you will, of the condensed structural formula. There's this guy, or you're going to see this as well. You know, what's your job? Your job is you need to recognize the fact there's a hydrogen and a chlorine there. This is not carbon and iodine, or carbon or little l. There's no element little l. So this is chlorine in here. You got to recognize that. That means that these 2 atoms are bonded to that particular carbon. Remember, anything that shows up on the right-hand side of that carbon is what's going to be bonded to that carbon. And so what I've done here is, I guess technically, well, I don't know if there's some big definition in the official nomenclature book somewhere, but I guess officially that may be the condensed structural formula where everything's placed on one line. But But typically what I do is I mix the two methods together. When you introduce a new compound or a new atom, you introduce a new functional group. And like I said, I want to talk about these. These are haloalkanes here. And the second lecture talks about functional groups in more detail. You know, I've introduced a new atom, and oftentimes what I'll do is I'll use the expanded structural form around the particular functional group, because that's where the chemistry occurs, and that's where that's something I want to emphasize whenever I'm teaching this material. And so typically I don't use this. The textbook uses this, and you may come across it in the lab that you have to do, but typically this is how I'll write all the functional groups. I'll expand out over that new atom that's been introduced into the compound. The last thing I want to say about the isopropyl chloride is, well, let's see, let me just use green. There was another option in terms of replacing a hydrogen. I could have replaced, let's say, that hydrogen. And notice what happens now is that I get a different compound. Like that. Or I could have drawn the line there to indicate the chlorine was attached to the carbon. And again, anything on the right-hand side is attached to that carbon. You know, here, these are two different compounds. They're actually referred to as constitutional isomers. Next presentation is where we get into that. I just wanted to mention it while I was thinking about it. And, you know, go ahead and expose you to the term, at least here. And again, you know, they're different. They would have different names. This is isopropyl chloride. This is propyl chloride. And we'll worry about naming the haloalkanes later on. But they're slightly different chemical properties, slightly different physical properties. Now, these two are so similar that the difference isn't that great, but it's noticeable. They do behave differently depending on what they're paired up with. Notice that they share the same molecular formula. It's just a different connectivity between those 11 atoms here. They're connected two different ways, and it dictates their function, their physical and chemical properties. But again, in the second video is when I start talking about constitutional isomers. There's a few types of isomers that we have to worry about here, and I'll give a full treatment later on. You know, right now I want to sort of begin talking more, I guess. Unique compound, unique name. There's a big deal about nomenclature. This is one of the first hurdles that you have to get across when you're taking organic chemistry. When I took organic chemistry as a college sophomore, our first few months, it felt like, first few weeks anyway, was solely dedicated to nomenclature of all the different functional groups. That was the first thing that I had to do. And now I teach the class differently. I chunk the nomenclature according to the functional group that we're studying. So anyway, a little bit different. Which way is better, I'm not sure. But anyway, nomenclature is a common theme throughout organic chemistry, both semesters. And the one thing about nomenclature is, I guess the central feature is that longest carbon chain. And what I mean by longest carbon chain, I mean that one continuous stretch of the longest single continuous stretch of carbon atoms that you see here. So, and it's not always going to be what's written straight across the board. You know, you can clearly see that these 6 atoms, they're just longer than these 3 or these 4. And it's the longest carbon chain that dictates how we start constructing the name. Okay, and actually the names are given here. Let me just sort of break it down here. So this part would be the base. This portion would be the suffix, and then this front part is the prefix. And it's the substituent groups, which we're going to spend a lot of time learning. And again, I mainly just want to break it down. I don't want to get into too much detail here. And then the same thing here. This is the base. And then, you know, whatever's in front of the base is the prefix. Whatever's on the right-hand side of the base is the suffix. And notice what they're telling us here. So let's take a look at that. What family? Well, in both of these examples, we have an ANE ending, and that is corresponding to the family or functional group, that's what they're talking about here, of alkanes, which is the first hydrocarbon that I introduced to you, this guy here. And this is really what's going to spend most of our time. Notice that the name of this compound, ethane, it has an ANE ending. That tells you automatically it's alkane. There's a change in the ending if you change a functional group. It's the systematic way of naming compounds. And so, I don't know, in your typical 2-semester course of Gen Chem, you're coming across, I guess, around a dozen different functional groups or so that you really get into. Maybe a little less, a little more, depending on who's teaching the course. But in each one of those functional groups, there's a slight variation in the ending, and it tells the student or the organic chemist what kind of functional group you're looking at. And then the base here is telling us about the longest carbon chain, the LCC. And you can see here there's 6 here. Well, hex is like a hexagon, or a 6 in, I guess it's the Greek alphabet is hexa, and so for the vast majority of base portions of the name is coming from a Greek or Latin root. There's a few that don't follow that particular pattern, but I'll show those here in a minute. In this particular example, notice that the longest carbon chain was quite a zigzag in this particular molecule, but I found it, or the book found it. There's 7 carbons connected together in a series. And, look at the other options. I see sort of a long one there. Let's count them up in blue here. 1, 2, 3, 4, 5, 6. So, 6 is less than 7, so it's not going to win out. Because this base name is telling you how many carbons you have in the longest carbon chain. And in this case, notice that hept, that's coming from hepta, which is 7 in the Greek, I believe. And then, what it does is it establishes what I often refer to as the parent name for the compound. So it establishes the longest carbon chain and what kind of functional group you have there. You have all carbon single bonds in this molecule. It's a saturated hydrocarbon. And then anything out front, what it's doing is showing you what's in red, what are referred to as substituent groups. These are just branches coming off the longest carbon chain. Now I'm not going to break this down yet, and except for at least notice the numbers here. There's a particular way that we number these longest carbon chains. I'll talk about it here in a minute. But the 3 and the 2 and the 4 and the 5, all that is doing, it's showing you where on the longest carbon chain you have substituent groups showing up. The 2, the 3, the 4, and the 5. And we see those numbers being spread out, a certain method, in the prefix portion of the name. Okay, so let's look at some of these examples. Now, I guess the title of the slide is actually telling you the punchline, right? These are equivalent. These 2 molecules are equivalent. And they're both condensed structural formulas. One is probably the mode that I would use. Typically when you come to a branching point like you have here, or a functional group like we had, back here with these haloalkanes, I'll expand that structural formula. And so that's what they're doing in the top example here. But these are equivalent. Let me show you what I mean by that. The first point of understanding a molecule oftentimes is finding that longest carbon chain, and then for a lot of these is what's written straight across the page is going to be the longest carbon chain. That's the easiest way to teach this initially, I think. But there's 6 carbons here. There's these 2 groups, which are referred to as methyl groups. This is one very common type of substituent group that you have. Remember, a substituent group is just a branching point, something coming off the longest carbon chain. Now down here, it's at more of a condensed structural formula. Remember, it's the type that I'm not going to use very much, but you will come across it. And what they're doing here is to indicate that you have a substituent group. They're actually putting parentheses around the different substituent groups. So it's telling you that it's a branching point. Again, whatever's attached to that, whatever's on the right-hand side of that carbon is attached to that carbon, but they're showing it in a single line. And so if I apply this, this game of looking for the longest carbon chain, 1, 2, this is not 3. You have to remember, when you see the parentheses in these alkanes, this indicates a branching point. It would look like that. That would be 3. Here's another branching point, 4, 5, 6. And notice the pattern is the same in both of these structures. In the blue down here, you have 6 carbons of the longest carbon chain. Here in the red, you have 6 carbons of the longest carbon chain. And then at the number 2 position and at the number 3 position, in both of these drawings, you have methyl groups attached to them. Same pattern, same compound. It's a unique compound, even though it's drawn differently. And it would have a unique name as well. And I may come back to this once we get through a little bit of the nomenclature rules here. But, notice, remember what I started with on this structure. I look for the longest carbon chain to start establishing its relationship to this structure. And so again, the LCC is very important to be able to pick out in one of these molecules. Without doing that, you're not going to be able to name the thing. Whether it's an alkane, an alkene, an alcohol, any functional group that we come across for this subject. So what about the longest carbon chain? Well, you have 6 of the longest carbon chain here, and just like before, that example before, hexane was showing up as what I was calling the parent name. There's the base name, there's the prefix. There is a table of these, and it's on the next slide. Here we have them. And what we're doing is we're beginning to build our foundation for understanding nomenclature. And so let me just sort of take a little tour of this table and sort of pick it apart. What is it telling us? Well, there's the molecular formula, and that's fine if you want to talk about like a balanced combustion reaction of alkanes. You can just use these things. If you don't care about the structural feature of the molecule, then you can just as easily use the molecular formula. But are we going to do that? No. We're going to worry about the condensed structural formula. So in each one of these, what they've done is they've spread out the number of carbon atoms in the molecular formula as a straight line, and then they've saturated the molecule, if you will, with hydrogens around it. And so look back at, there's a propane that I did a few minutes ago. And remember, again, whatever's attached, whatever's on the right-hand side of each carbon is attached to that carbon. And I'm just going to go ahead and transition to the condensed structural formula as shown. I'm not going to go back to the expanded structural formula. It just takes up too much room and too much writing. I write enough of these molecules having to go through the expanded structural formula. And these, I guess you would, yeah, oh good. The straight chain alkane series. What they mean by straight chain is that, well, there's no branching point. This is, if I looked at these 10 carbons, like in a three-dimensional structure, actually what they would look like is a series of zigzags, because they're all tetrahedrally shaped. But of course, in the condensed structural formula, they just look straight. There's no parentheses in here, so it doesn't indicate any kind of branching. There's no lines drawn dropping up or down from any of the carbon atoms, so there's no branching in this molecule. That's what they're referring to as a straight chain, no branching. And then the main thing about this table is this guy here, the use of the names. Now the prefix, well, it's the same all the way through. We're dealing with the alkane series. ANE is dedicated to an alkane. What's changing here, we have a unique molecule at each step along the way here, and so we'll want to generate a unique name. That's just something that you're going to see for any chemistry, whether it's organic chemistry or even inorganic chemistry. You know, sodium chloride, sodium bromide, well, I mean, part of their solubilities are very similar. Chemically, they're very similar, but unique compound, unique name. So we're really not introducing any new broad notion here. We're just sort of focusing in on the organic nomenclature at this point. Now, to pick apart the name, let me point something out to you. 5 carbons down, you're using the Greek prefix. That's good. I like that. You've already learned those, actually, in Gen Chem 151, the first Gen Chem. Whenever you're doing let's see, P2O5, like diphosphorus pentoxide, we're using the Greek prefixes to name those. And so this shouldn't be that new to you. These up here, though, however, they are new. Meth for 1, eth for 2, prop for 3. You know, we saw that in the previous example. And then bute, not but, bute for 4 carbons. Now, what the origin is for these 4, I'm not real familiar with. I do know that for, again, you know, speaking Latin was a sign of an educated person for, you know, 400 or 500 years in the Western world. So it's not unusual to see Greek and Latin roots all over chemistry. You know, Oxford University, you know, as of 1971, it was one of the requirements for freshmen was that they were fluent in Latin. So, you know, this feature of the Western world is carried over into many different fields, especially in science. And so, you know, hence you see the Greek prefixes here for the numerical values. The only story that I know that I've heard, and I believe it, this bute prefix. Let's see. I think I can deuterium, not deuterium. Doing this in my office, I have my books right here. BUTYR. That's Latin for butter. Okay, you know what we have here is so when butter goes rancid, one of the nasty smelling compounds is butyric acid, and it's called a carboxylic acid. It's like acetic acid, carboxylic acid with 4 carbons total. And so my guess is that, you know, somewhere in the 1800s, when they're starting to figure out what is that smell, what is that compound, they found 5 carbons in that molecule. And so what do? We find that BUT prefix going back to the Latin root for butter, showing up in our nomenclature. And I wouldn't be surprised if there was some story like that associated with each one of these. Who knows? But anyway, you just got to know them. You have to know this chart. You have to know the name here and then the corresponding number of carbons in the alkane series. The physical properties here, boiling point, the only thing I'll say right now is just notice that the boiling point increases as you increase molecular weight. That's something you should know. So as the molecular weight increases, then boiling points and melting points, the physical properties, you get a corresponding increase. As these things get larger, well, what happens is their intermolecular forces increase, specifically dispersion force. And we may talk about that. And I know that on the next presentation there's a slide dealing with it. And so we'll talk a little bit about it as we get a little deeper into the subject. Okay, let's apply this chart to a few examples. And what I'm trying to do is sort of lead you through the method for naming these compounds, how to construct the prefix, base, and suffix. Well, I guess the base and suffix, we've already seen all the variations that we're going to find for this first lecture anyway, and they're coming from the names of you're going to see these repeated many times, many different ways, because right now we're just dealing with saturated hydrocarbons. So remember, you know, that would be the base. Meth indicates 1 carbon. A and E tells us it's a functional group, so there's the suffix, there's the parent name. And so you're going to see these repeated a lot. Know these, okay? That's simply put. And again, focus on the longest carbon chain. That's very important. Now, again, because the longest carbon chain, what it does, it establishes this parent name. And without the parent name, you can't do anything with this particular subject. So I think on these examples, I've placed the longest carbon chain along the horizontally on the slide. And in this example, I have 1, 2, 3, 4, 5 carbons for the longest carbon chain. Actually, 1, 2, 3, 4, 5. Notice there's actually 2 longest carbon chains. As it turns out, as long as you find the longest carbon chain and you apply the rules that I'm telling you, really it doesn't matter whether you number this longest carbon chain or that longest carbon chain. It's going to give the same name. You sort of need to trust me on that, okay? As you do more problems, as you get more exposure to it, you realize that statement is true. So just have faith in what I'm telling you. As long as you follow these rules, you'll come up with a unique name. Now I'm going to concentrate on the 5 carbons just written horizontally across the screen. That's a little bit easier. And remember, just like we did a couple slides ago, there's an issue about how you number the longest carbon chain. You need to establish, addresses, if you will. 1, 2, 3, 4, 5 on this molecule so that you can tell me where the methyl, and now this is referred to as the ethyl group. I'll do a little bit more formal song and dance on these later on. I just sort of want to get through the construction of the names here. But those numerical value on the longest carbon chain establishes the positions where these different substituent groups show up. So the rule is, here I have an issue. Do I start this as a number 1 carbon or that as a number 1 carbon? And the general rule is you try to get the lowest numbers possible. That's just an observation that I've made. And the rule states you number the end closest to a substituent group. Well, if I started here, it's 1, 2. If I numbered here, it'd be 1, 2, 3. I'd have to go to 3 carbons before I find a substituent group. And it doesn't matter if it's ethyl or methyl in these examples right now. So what it does, it tells me that I established the numbering of the longest carbon chain at this end because I keep the numbers low. I keep this one as the first substituent group at the lowest number. And now what I can do is now I have enough information to construct the name. So I know the parent name. It's going to be pentane, 5 carbons with the A&E ending for saturated hydrocarbon. What I want to focus here is how to construct the prefix. And one thing to keep in mind, it's always alphabetical order. That's important. E comes before M the last time I checked, so the ethyl group is actually going to be listed before the methyl group. So you don't worry, you number it to establish a position, but the number does not dictate how you lay out the name. Let me show you what I mean by that. There's our complete name for this compound. So again, E comes before M. That establishes that ethyl comes before methyl. And then I've just dropped down the numerical values for the address into the name here to establish where on the 5 carbon chain these different substituent groups are labeled. Last thing, for this particular example, notice that I have a transition from a letter to a number, and then you use a hyphen whenever you see that. So again, between a letter and a number, you always throw a hyphen in there. I guess that would look better. Letter, number, you always put a hyphen. And later on, we're going to see if you have a number to a number, then you drop a comma down in there. Okay, so just a little grammatical rules here. Okay, so that's one example. Let's look at this example. Again, it's a little bit more complicated. We popped up a new rule. Why are there so many rules here? Well, we want a unique name for a unique compound. Each compound, even though there might be just a slight different shape to it or additional atom, it's going to have a different set of physical and chemical properties. It may not be that much different, but it's different. And so we want to establish a a different name for those different compounds. And so, as you get into this, you see more and more rules being applied. Now here, again, 1, 2, 3, 4, 5. So I've stuck with pentane on this example. Keep the parent name the same. But I have an issue. If I number the longest carbon chain, 1, 2 here, let me just, actually, this is going to be the proper way of numbering the longest carbon chain. So 1, 2 this way, I hit the first substituent group. But if I had numbered it on this end, 1, 2. So in this particular molecule, notice that it doesn't matter which way I number on either end. If I just go by this rule, the first substituent group is still going to show up at the number 2 position. So you have to have an additional rule because you need to establish the proper way of numbering the longest carbon chain. And that is the side with the closest to the greatest branching is what you look at. So notice what I mean by that is that there's 1, 2 branching points at this carbon, and then if I go in 1, 2 positions from the other end, there's only one substituent group, one branching point. And so this greater branching establishes the orientation of the numbering. And then to lay out, the parent name and then the substituent groups, it's the same rules as I used before with a few additional aspects. Let me construct a thing. They're all methyl, so there's no issue of alphabetical order. Alphabetical order comes into play if there's ethyl and a methyl. If there's two or more different substituent groups, then you got to worry about the alphabetical treatment of it. But let me just construct the name. I think that may be the most useful way to take a look at it, and then I'll break it apart. Please note, parent name is the same as before. We have a longest carbon chain of 5, and then we're looking at an alkane. The substituent groups. So yeah, I have methyls in there, but I have 3 methyls. So tri stands for 3, di would stand for 2, and sometimes you might see tetra as 4. Those 3 are the most common ones. These two are the most common ones that you're going to come across for this class. However many substituent groups I have here, I have 1, 2, 3 different substituent groups. I need to indicate that in 2 different ways in the name. I see the tri here tells me I have 3 methyl groups, and then notice that at each position along the longest carbon chain I add a number. And yes, 2 methyl groups at the number 2 position, a 2 and a 2. You've got to have 2 2s in there. Okay? So each methyl group, each substituent group is going to get a corresponding number in front of the name of that substituent group. And like I said before, if you're separated by numbers, then you put a comma. If you get the transition from a number to a letter, then you put a hyphen. So just keep in mind that, however many substituent groups, you got to account for it 2 ways. The di or tri in front here, and then for each one, it's a different number. Okay, so if you left out that 2 there, and it's just 2, 4, that doesn't work. Okay, and the reason why that is because when I see trimethyl, I know I have 3 substituent groups. I have 3 methyl groups on a 5-carbon chain, and I really don't know where those branching points are. By making it very explicit, by saying every single number that you see here on that diagram, I know exactly where those 3 methyl groups are going to show up. I know that 2 are on the number 2 position, and then the third one is on that number 4 position there. So that's why we need all of those numbers. If it was just 2, 4, then it doesn't account for, it only accounts for 2 of the methyl groups. And that third methyl group could be anywhere in the central part of this molecule. Okay, so this method here ensures that there's no ambiguity, if you will, in the name that you have there. Okay, another example. Let's see. I have changed this up. This is a 6-carbon chain, and so I'm going to go ahead and number it correctly. And actually, notice what I'm doing. I'm starting from the other end this time. I wanted to change it up just a little bit. 6 carbon, so hexane is going to be the parent name. Why did I number it from that end? Well, the first 2 rules. Actually, let's just look at the second rule. You 1, 2, 3 in 1, 2, 3 in. From either side, I come to a substituent group at the number 3 position. Again, if I had numbered from here, 1, 2, 3, that carbon, there's a substituent group. So that rule doesn't work because there's a single branch at each point. So what's the rule? So if there's equivalent branching, i.e. one branch at 3 carbons in from either side, then you see the alphabetical order kick in. We have to use something to establish the orientation of the numbering. Remember, this is a methyl group, CH3 is a methyl group, and then CH2CH3 is referred to as an ethyl group. And so that's why I started numbering from this end, because E comes before M. Alphabetical order establishes the numbering for this particular molecule. Let me construct the name. Alphabetical order establishes a numbering, and then, like I said before, the alphabetical order also establishes how I lay out the substituent group. So, for example, it would be 3 ethyl, 4 methyl, and this one again is hexane. We see our hyphen between numbers and letters on both sides and in front. Alphabetical order is showing up just like before. And again, this example, equivalent branching at the number 3 position in from either side, then we have to use alphabetical order to establish the numbering system. The best way to learn these things are to practice these molecules. So there's one for you to practice. I would recommend, either rewatching the last 3 slides or so and then giving a shot, or just going at it and see what you come up with. Pause the video and then restart it, and I'll do the answer. Okay, so here's my compound. Let me see. This one thing to note is this is not a longest carbon chain along the horizontal. There's only 4 here, there's 3 here, there's 2 here. And there's clearly, there's 3, 4, 5, 6, 7 in that particular chain. What I want to do, I think I found the longest carbon chain. Here, here, and here. So in blue, I've just highlighted what appears to be the longest continuous stretch of carbons that are bonded together is what I'm looking for. And then notice there's 2 of these that are not highlighted in blue. I want to put a box around these guys. These are the substituent groups. Okay, so I found the longest carbon chain. Let's look at how we number it, because, numbering from this end and numbering from this end is going to establish 2 different sets of numbers for these 2 substituent groups. For example, if I started from this end, 1, 2, 3, at the 3rd position on the longest carbon chain, then I come to this methyl group. So that's at the 3rd position. If instead I started numbering at this end, 1, 2, 3, 4, well, now at the 4th carbon, that's where I see this substituent group. Okay, well, what's the rule? It's you number the end that's closest to the substituent group. Well, 3 is smaller than 4th. This one here is closer to the end than this guy. So I don't want to number from the bottom end here. I want to number from the top end. 2, 3, 4, 5, 6, 7. Okay, so I've established my parent name. It's actually heptane in this one. And then I need to so I've got the base and suffix in this heptane name. Now I want to worry about the prefix. That's all the substituent groups. Remember that we need numerical values here for the positions of the substituent groups. We have 2 methyl groups here. We want to be very explicit in terms of what we have in the structure. And so what we have is at the 3 and 4 positions, we have 2 methyl groups, and they are on a parent name of 7 carbons, is what this is telling us. And so, again, you see that pattern. There's our Greek prefix to tell us how many methyl groups. We have 2. We need 2 numerical values, hyphens between numbers and letters, commas between numbers. And that's the proper name for this compound. Numbering from this end would have been incorrect. Then it would have been like a 4,5 dimethylheptane. I mean, I guess if you use that name, it would still construct the same molecule, but by establishing this systematic way, then we've set up a set of rules where we're guaranteed no ambiguity, no confusion about the name of one compound from one compound to the next compound. Okay, and so in the next few presentations, what we'll do is we'll look at the different functional groups and we'll learn how to name a few more of the functional groups. But even when we name those other functional groups, we're going to use, we've established a pattern, we've established a systematic method for naming organic compounds, and we're going to see these set of rules used in a variety of ways for the next few functional groups.